So, the hook for today has to do with the skills of you young drivers and what effect it has on your stopping distance to double your driving speed. Does it make your driving speed square root of 2 times as long if you double your speed, or 2 times as long, or 4 times as long, or 8 times as long? Please again put your answer on the quiz, and feel free to go back as we go through this lecture and change that answer as you get information that gives you a more informed choice. So we are stopping. That is a negative acceleration and negative change in your velocity, and we need to define acceleration. And it is defined as the rate of change in velocity. But velocity is itself the rate of change in position. So acceleration then is a rate of a rate, which makes things a little bit awkward. In particular, if you look at the units of acceleration, meters per second are the units of change in velocity per second. So meters per second are acceptable units for acceleration. If you take meters per second and divide them by seconds, often when we work with fractions and division, we prefer instead to multiply by the reciprocal. And you can see if you multiply these two together that you do get meters per second squared, which is perhaps the preferred, although this is equally good. Most often you will see this written as the units of acceleration. Oh my, graphs again, but this time not position time graph, but velocity time graph. If we consider that in a velocity time graph, the slope, rise over run, the rise would be change in velocity if it's velocity on the vertical axis, and run again is time. So the slope of a velocity versus time graph is by definition the acceleration. So what you're going to be doing here again is to look at the slopes. Don't look at the fact that the velocity is increasing. Look instead at what the slope is doing in this region, and whatever you can say about the slope in that region, that is what is true about the acceleration. So I want you to look at these 4 numbered velocity time graphs, and for each of them, pick from the letters P, Q, R, and S, which letter goes, which acceleration time graph is associated with each of these. And if you could do that on your quiz, that would be excellent. Now we introduce formulas for doing problems with acceleration. And the first formula is not a new formula. This final velocity is equal to initial velocity plus acceleration times time is just an algebraic manipulation of the definition of acceleration. Change in velocity, velocity final minus velocity initial, and then I multiply through by t and add velocity initial, and bingo. So this is not really a new formula for you to memorize as long as you have memorized the definition of acceleration. The next formula having to do with displacement under the situation where there is acceleration, and by the way, very important, this acceleration is constant. I have a value to put in for a, and these formulas only work under conditions where you have constant acceleration. You will encounter this year situations where the acceleration is not constant, and you cannot use these formulas under those conditions. But this formula here is not as pretty as that one there. It's got this awkward 1/2, it's got this extra term, and many people mistakenly would prefer to use this equation. I'm writing it in red because it is wrong, and red is the color of wrong. Sorry, all you redheads. Many people would prefer this equation for the relationship between acceleration and displacement. And unit-wise, it seems fine that this is meters here, and here is meters per second squared. And so if I multiply this by seconds squared, bingo, everything looks good. But it is a mistake to call that a formula. Taking distance and dividing it by time squared does not get you acceleration. Those are the units of acceleration. That is not a formula for acceleration. Here is the formula for acceleration. This is the formula for displacement and its relationship to acceleration. And it's the only formula there is. The other mistake that people like to make is to say that delta x is equal to vt. That is a big mistake too. That correctly done, delta x is equal to the average times t, which is not at all the same as v initial times t, or v final times t. You need to be very careful. This is a very comfortable formula. It's one that you have used in rate problems in math over and over again. But what you ought to do is to write this formula from now on. You need to start memorizing it. If indeed there is zero acceleration, then there's no change in velocity, and the initial velocity would be the same as the average velocity, would be the same as the final velocity, and so this formula would work. But don't go directly to this formula. Start here, and then confirm for yourself that the acceleration is zero. Never, never, never use that formula. In fact, I think it is time to make these formulas go away. They're wrong. Do not focus on them. Oh, so much time to make them go away. Come on, go away. Distraction be gone. All right. Oops, still a little errant s. S. All right, without distraction, we focus on this formula. Its derivation, in case that makes you feel better about it, goes like this. That if you have constant acceleration, which again I emphasize is the only way you can use these three formulas I'm about to give you, under the conditions of constant acceleration, I claim that this is true, that the cover things up. Because it is constant acceleration, the graph is going to have constant slope, which means it's a straight line, and only under those conditions is it true that the initial velocity plus the final velocity divided by 2 is equal to the average velocity. That is not in general true, but that is always true where you have constant acceleration. So, given that, I then take this formula and I put in for v average the definition of average velocity. Then I'm going to take this expression here and I'm going to subtract v initial and add v initial to it, which seems like a strange thing to do, but it is, after all, 0 that I'm adding on, so it's legal. And then we have v initial plus v initial, that's 2v initial divided by 2, that gets us v initial, and v final minus v initial times 1/2, and then I'm going to take that and multiply it and divide it by t. which again seems like it's doing nothing, and that's the idea. I'm not changing anything here, but if I take this t and divide it into v final minus v initial divided by time, that's acceleration times time. And so then what you have here is multiply through this equation by t, and you have this equation, which is the one that I gave you. It may seem awkward. It is the way our universe works. Get used to it. Memorize it. When you're doing homework problems, don't go back and look up the formula. Try to pull it out of your head, and then go back and check and see you pull it out of your head correctly. But very quickly you need to get to the point where you know these formulas like the back of your hand. This final formula will be very useful to you, but it is not necessary that you learn this formula. This formula is just the simultaneous solution of these two, getting rid of the time, that I solve this equation for time, take this equation, solve it for time, put that in for time in the second equation, boom, boom, and then do the squaring, and things get very, very awkward. Sort out the algebra, and when the dust settles, it'll look like this. A lot of problems will come up where this will be a very nice fit to the data that's given to you. I strongly encourage you to memorize this formula to avoid going through the simultaneous solution of these two equations. In your book, there are two more equations. One where we have solved this equation for VI and substituted it in here, so we get an equation which doesn't have VI in it. This one doesn't have delta x in it. This one doesn't have V final in it. Doing that substitution I just mentioned, you get an equation without VI in it. This one doesn't have time in it. And finally, you could solve this equation for A and put it into here and get an equation that didn't have A in it. And the book gives you all 5 of those, but the last two do not come up often enough that it is worth your brain space to memorize them. I would instead, when that situation arises that you need to work and they haven't given you acceleration, do these two equations simultaneously so that you can substitute out the missing acceleration value. All right, so here's a problem. Here are the equations. I've written them here so you can just refer to them immediately, but you do need to memorize them. They will not be written for you on the test. So you have to practice as you do homework, working without this crutch. So here's a word problem, and many of you may love word problems and feel very comfortable with them, but some of us get confused by them. They are inherently confusing because they're stated in English, which has many ambiguities about it. And it is the most important part of problem solving, and I feel this very passionately, to figure out those ambiguities, to figure out what have they told you? What do I know? And equally importantly, where am I trying to go? What is it that I'm trying to answer? This extends far beyond physics. As I said, I get passionate about it. This is problem solving all over the place. You want to solve homelessness. You want to solve, to accomplish world peace. Well, you cannot go about solving those problems without first figuring out where you're trying to go. What does it mean to solve homelessness? Surely you don't mean assassinating all homeless people. So what exactly do you mean by the solution to homelessness? And then, what do you know about the causes of homelessness? What do you know about mental health and property possession that could then be used to get to the place you're trying to go? You're having a problem with your spouse and you would like it to go away. What does it mean for it to go away? What does a happy home life mean to you? where are you trying to go, and also, what facts do you have? What psychoses does your spouse have that need to be taken into account as you try to find a solution to the problem? All right, less prosaic. This problem here. Words, words, words. I want to get rid of words and just have numbers. And so I look through here. I discover a number, 5.5. I write it down, and then what is it they've told me with that 5.5? And I could either look at the units for a clue, or I could read carefully. It accelerates at 5.5. So that's acceleration. Do not write out the word acceleration. We're trying to get rid of words. Choose a symbol and use a symbol that fits with the tools that you have. Similarly, 28 is a number. Boom! What is that? Well, that would be velocity. Looking at the units, it's velocity. I would not want to call this speed, because speed is not contained in these equations. This is a mistake. It is incomplete. This is what I would refer to as a naked velocity. Here are velocities privates right here, and they need to be clothed. It is just embarrassing to have a velocity without something here that you need to call it velocity initial or velocity final or velocity average. Or we saw just a minute ago that the mistake that you make if you just assume velocity is velocity and it could be average or initial. You could call it velocity 1 at time 1 or something like that. Well, which one is this? We need to not leave this velocity naked. And how long are we required to reach? To reach. So it wasn't there, and at the end it had made it there. So we call that the final velocity. Very important. Notice I'm also leaving off units, because that's more stuff to look at, and it will confuse me. Sometimes S's end up looking like 5s. As long as the units are fundamental MKS, don't write them. Now, if this was in centimeters per minute, then I would want to write that, and probably I would then want to convert it into meters per second so I could use it together with the acceleration. And finally, the question. How long? There's the question, how long? So length is going to be displacement. And this is the problem I'm trying to solve. And suddenly you feel a little bit awkward because you don't think that should be delta x. That in fact, Mr. Houghton, how long? Length is distance, right? Meters. No, in English, Mr. Houghton, sometimes how long means how much time. So in this ambiguous statement here, were they talking about how much distance must be covered before you get to 28, or how much time must pass before you get to 28? And it's not entirely clear. But you, in your human capacity to make decisions, may decide that time is more what the author intended when they wrote that problem. Not straightforward stuff, this pulling the information. I need clever and talented humans to take this and interpret. A computer, once I get these numbers, a computer will get me the answer. I don't have to think anymore after I get these numbers. But figuring out what I've been told and where I'm trying to go with it, I need your talents for that. And so I should give you a lot of credit for doing that. I should give you, and yea, verily, I will give you 80, 90% of the points in this problem for just telling me what the problem asks and where it's trying to get you to go. Because I claim that once you've done that, you just fit these numbers with this data, these tools here, and the answer is done. I don't need you anymore. But I do need you to do this and should give you maximum credit. I think this is the problem solving right here. Figuring out what you know and where you're trying to go with it. All right, but let's finish it out. So I have final velocity and time. This equation has final velocity, doesn't have time. This one has final velocity and time. So there is the tool that I want to use in doing this problem. And, oops, sorry, I'll write it down. Now this is what I'm calling the Houghton method of problem solving, or a la Houghton. And in this unit, you must do it this way. If you discover that this is cumbersome and it gets in the way of your innate ability to solve problems, after this unit is over, you can go back to your other way. But I think it would be a big mistake. I used to do it not this way. I would kind of scribble in the margins, and then I would get an answer. Truth be told, the reason I scribbled in the margins and didn't write it out clearly, because I wasn't entirely sure what I was doing. And I was hiding my confusion from myself. And so do I think you are when you do not write it out this way. It's showing that you have ownership of what the problem is and how you are working on it. Write this in symbols. And then, having written it in symbols, underneath, substitute in. I'm sorry, I didn't finish a thought. So after this unit, you don't have to do it this way anymore if you don't want to. But that 80% of the points I said I was going to give you for figuring out what the problem is and what tool will work with it, you will not get if you just put down an answer and the answer is wrong. So I would strongly encourage you to adopt this approach for the duration of this course, nay, verily, for the rest of your life. So here I am. I've written this down, and for the final, oh, we don't have to be read anymore. We have 28. Right underneath, I substitute it. And for the, the initial. I need the initial to use this equation, and I don't have the initial. What am I going to do? It's the only equation that has V final and time in it. What am I going to do? I go back and I read the problem again very carefully. Oh, there it is. I missed it. From rest was telling me what the initial velocity was. That the initial velocity was 0. I really feel that this approach to problem solving led me to the fact that I needed to know initial velocity, and then I went looking for it, and there it was. Okay, so the initial velocity is 0, and the acceleration is 5.5, and the time is still unknown. Now, this far is as far as you need to show me. If you want to show me your work in solving for time, you may. But if it all happens in a calculator at this point, it's fine for you to show me nothing. Then your calculator tells you that 28 divided by 5.5 is 5.090909, and that's ridiculous. You go back to the original problem, look at 2 sig figs, and so you report your answer as 5.1. And then put the units on it as well. Correct sig figs, correct units. What a great job of problem solving we have done. And now we'll try our hands at it. Please take on this problem. If you can, try to ignore that that is there and see if you can guess at the tool. But first you need to pull the information, make it a vertical list. Do not write these things horizontally across the page. Let's go back here. Make it be vertical. I want these truths that I have to stand out to me. If I write it horizontally across the page, they blur together. Vertically, please. Okay, so pull the information. In addition, one of the very important pieces of information is what question are they asking? And be sure you state, don't write how high for the question. State it as one of the variables that fits these 3 tools equals question mark. Then find the tool that fits the data that you have and get me an answer to correct sig figs and units. And then do it again on this problem. Again, trying to see if you can pull these without looking at them, but then check and do it a la Houghton, please. Finally, a little challenge. By the way, in that, I'm sorry, it's too late. When you're doing S and T, please do it a la Houghton, and you have space, I think, on the sheet to do that. Here is this Mary who slams on the brakes, stops her car in 4 seconds, and then takes twice as long, 8 seconds, to get back up to the initial speed. So that's definitely accelerated motion. She has a negative acceleration and then a positive acceleration. That, I would point out, is half as much. The rate takes her twice as long here. So which one of these pictures, if this is Mary's car, and every 2 seconds there's a flash from a strobe, and you can see where Mary's car is at these points, which one of these 4 choices correctly describes the scenario up there? And when you are done with that, you are done with this lecture, and thank you very much.